Welcome to our quantum deep dive. Today we're talking about a device that sounds like it's been ripped from the pages of a sci-fi novel, that it is absolutely real and, actually, a cornerstone of modern physics. We're talking about an invisible cage, a microscopic prison designed to hold some of the most elusive particles in the entire universe. I mean, just think about that for a second. How do you possibly grab onto something that annihilates the very instant it touches regular matter? You can't just, put it in a bottle. Well, we're going to answer that exact question by diving into the incredible technology that makes it all possible, and it's all based on a fantastic essay by Jorg O.A. Schneppot. So here's the plan. We'll start with the big picture of what this quantum cage even is. Then we'll break down exactly how its clever combination of fields actually works. After that, we'll get into the really cool stuff, its incredible applications, and we'll even compare it to its main rival. And finally, we'll take a peek into the future of this amazing trapping technology. All right, let's get into it. So what is this device we're talking about? It's called a penning trap, and its entire reason for being is to solve one of the most fundamental problems for physicists. How in the world do you isolate, hold, and study one single charged particle in a perfectly controlled space? You can really just think of it as an invisible bottle for the tiniest things you can imagine. It gets its name from the Dutch physicist Frans Michel Penning for his work way back in the 1930s. But the modern version we use today, well, that was perfected by Hans Georg Dehmelt, who actually won a Nobel Prize in 1989 for his work on ion traps. That really tells you how important this device is to physics. Exactly. So how do you build an invisible bottle? I mean, you can't use physical walls, obviously. Instead, it all comes down to this carefully choreographed dance between two different kinds of invisible fields. One is magnetic, and the other is electric. Let's really break down how this dance works. Okay, so first you apply a really powerful, really stable magnetic field that runs right down a central axis. This field basically acts like a leash on any charged particle that tries to move through it. It grabs the particle and forces it into this tight, fast spiral, which stops it from escaping sideways. This super fast circular movement has a name. It's called cyclotron motion. But here's the thing. That magnetic leash only works in 2 dimensions. The particle is still totally free to just slide right out the ends along those magnetic field lines. To solve that problem, we add an electric field. This field is created by 3 special electrodes, a ring in the middle and 2 end caps. This setup creates an electric potential that acts like a hill, always pushing the particle back toward the middle, basically capping our invisible bottle and trapping it in that final 3rd dimension. So when you combine these 2 static, unchanging fields, you get 3 totally distinct movements all happening at once. You've got that fast cyclotron spiral, then a slower bouncing motion back and forth between the electric end caps. That's the axial motion. And finally, this very slow, kind of lazy circular drift called magnetron motion. And this is the real genius of the design. These 3 stable motions create a perfect, incredibly long-lasting trap for one single subatomic particle. And okay, once you've actually trapped a particle, held it perfectly still in a vacuum, all by itself, you can start to ask it some really profound questions. And the applications of this technology, well, that's where things get really exciting and start to push the boundaries of what we even know about our universe. One of its most famous achievements has to be measuring the magnetic moment of the electron, which is also known as its G-factor. Using a penning trap, physicists have measured this property with an accuracy of more than 1 part in a trillion. Now, to give you an idea of how insane that is, it's like measuring the distance from Los Angeles to New York City and being accurate to within the width of a single human hair. It is one of the most precise tests of the standard model of particle physics that's ever been done, period. And hey, remember our opening question about antimatter? Well, this is exactly how scientists handle it. Over at the ALPHA experiment at CERN, they use penning traps to catch and hold antiprotons. They can then carefully combine them with anti-electrons to create antihydrogen. This lets them test fundamental laws of physics like CPT symmetry and even try to answer the question, does antimatter fall up or down? And it turns out that this incredible level of precision and isolation is exactly what you need if you want to build a quantum computer. A single ion, held perfectly still and completely shielded from the noisy outside world in a penning trap, can act as a qubit. That's the fundamental building block of quantum computing. From there, scientists can use lasers to very carefully manipulate the ion's quantum state, letting them store and process information in ways that our classical computers can only dream about. Now, the petting trap is amazing, but it's not the only game in town when it comes to caging ions. Its main rival is the Paul trap. It was actually developed by Wolfgang Paul, who, funny enough, shared that 1989 Nobel Prize with Demelt, and it uses a totally different principle to get to a very similar goal. So, the single most important difference is this. The penning trap, like we've seen, uses static, that means unchanging, magnetic and electric fields. You can think of it like a perfectly stable bowl. The Paul trap, on the other hand, uses a rapidly oscillating electric field. It's much more like trying to balance a marble on a spinning saddle. The average force over time is what cleverly keeps the particle trapped right in the center. And as you can see here, their different designs really lead to different strengths and use cases. The penning trap static fields give you this unbelievable stability, which makes it the absolute champion for hyper-precise measurements in fundamental physics. The big catch, though, is it requires a huge, incredibly expensive superconducting magnet. The Paul trap is simpler and cheaper because it doesn't need that magnet, which makes it perfect for more common things like mass spectrometry or for creating these long, beautiful chains of ions for certain quantum computer designs. So what's next for this incredible device? I mean, as powerful as the penning trap is, there are still some major challenges to overcome. But with those challenges comes some really exciting new frontiers to explore. Pushing the limits of physics means you have to overcome some immense technical hurdles. I mean, to keep a particle trapped for months at a time, you need a vacuum that is trillions of times less dense than the air we're breathing right now. The fields have to be shielded from the tiniest bit of external noise. Even a truck driving by outside could ruin a sensitive measurement. And trying to scale this technology up from trapping one ion to trapping thousands for a powerful quantum computer, well, that's one of the great engineering challenges of our time. But the future is incredibly bright. Researchers are working on integrating these traps into much larger, scalable quantum systems. They're pushing measurements to even crazier levels of precision, hunting for tiny little deviations from the standard model that could be a hint of brand new physics. They're even using them to create the world's most accurate clocks and helping redefine our fundamental units of measurement, like the kilogram. It really just leaves you wondering, doesn't it? All of this incredible science, these deep dives into the very nature of reality, it all comes from perfecting a way to hold on to just one single, solitary particle. By caging the smallest pieces of our world, we give ourselves the power to unlock its biggest secrets. That quote really is the perfect summary of this remarkable device. We hope this deep dive has helped demystify the incredible penning trap for you. A huge thank you to Jörg Schneppet, whose work was the foundation for this explainer. To read his original essay, please visit schneppet.ee. Thanks for watching.
Schneppet.de is a private project by Jörg Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.